Hello, this is Mr. Stansbury. I'm going to take you through the 9L notes on quadratic modeling. At the end of this, you should be able to say that I can solve real-world type problems represented by quadratic equations. Okay, so first thing, quadratic function looks like one of the two cases. It's a smiley face where y equals positive x squared, or it's a frowny face where y equals negative x squared. Okay. In this case here, this graph here has a minimum value because it comes down, as we're going left to right, it goes down, 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 down. At this point here, it's the lowest it'll ever be, and then it goes back up. So this point here is a minimum, and in this case over here, it has a maximum value. As we go left to right, we're going up, 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 until we hit this point here, which is the highest it'll ever get, and then it starts heading back down again. All right? So, the process of finding the minimum or maximum value is actually called optimization. And optimization is actually really kind of handy when you're looking at trying to maximize profits, or looking at minimizing costs, or maximizing heights reached, or areas and stuff like that. Okay, so let's take a look at that in a real world type example. Okay. So this is similar to example 34 from page 310, and this one is talking about launching some fish flops. So the height h in meters of fish flops t seconds after they're fired vertically upwards is given by h of t equals 80t minus 5t squared, where t is greater than or equal to 0. Okay? So, how long does it take the fish flops to reach its maximum height? Okay, so really what we're looking at here is we are going to have basically some kind of graph here. So this would be, say the graph here is going to look like, launch these flip-flops. They're going to go up here. This is where they hit the ground, right? Hit ground. And then this here is the max height, right? So it says, how long does it take the fish flops to reach its maximum height? So here's the maximum height. This here would be the time to reach the maximum height. So to do that, all we really need is the x equals negative b over 2a, because that's going to give us our axis of symmetry, which will also be the exact same as how long it takes these fish flops to reach the max height. So this is part A, so we get x equals, let's see, in this case here, a is the t squared, so a is negative 5, b is positive 80, and c is 0. So if we're going through to plug that in, we get x equals negative 80 all over 2 times negative 5. So that gives us negative 80 over negative 10. So that's going to take us 8 seconds. 8 seconds to reach the maximum height. Okay, so what is the maximum height reached by the fish flop? So if this here is the axis of symmetry, again we know that the x coordinate of this here is 8 for 8 seconds to find what the actual maximum height is, because this here, again down here is time, and then this is the height. So to find the maximum height, we'd actually just plug our 8 in to get what the y is, because that'll give us our maximum height. So let's see, part B is going to be to plug our 8 into our formula. So the height is going to be 80 times 8 minus 5 times 8 squared. Alright, so let's bust out our calculator for that to make sure that we get a good answer here. So, oops, that's weird. So 80 times 8 minus 5 times 8 squared gives us that our height would be 320, and I believe this here was all given in meters. Okay, so the max height of those fish flops after they're launched is 320 meters. That's pretty high. Well, it took 8 seconds to get up there, so that's, I guess, fairly understandable. I wonder what they're launching this thing with. But, sorry, last question is, how long does it take for the fish flops to make it back to Earth? Okay, so basically what you want to do is you want to find how long it's going to take to get back here. So how long is it going to take for it to land? So really what we're doing there is we are going to try to find the X-Intercepts, right? So we've got, let's see, h equals, I'm going to rewrite this as negative 5t squared plus 80 t, right? And so we want to know when the height's going to be 0, right? So 0 equals negative 5t squared plus 80. To make my life easier, 80t, sorry, I'm going to factor things out here. So I can factor, to make my life a little bit easier, I'm going to factor a negative 5 and a t out of both of these. So 0 equals negative 5t, and then that's going to leave this here with t, let's see, negative 80 divided by, 80 divided by negative 5 gives us negative 16, and the t's cancel. So t is going to have to equal negative 5 times 0 will give us 0, or positive 16. So handily enough, there's 0 seconds, and then here is 16 seconds, which is exactly halfway. It took 8 seconds to get to the top, so it should make sense it'll take 8 more seconds to get down to the bottom. So it's going to take 16 seconds to reach Earth again. All right. Okay. Let's take a look at one more example, and then we will call this good. All right. Let's take a look at this one here, example 35 from page 311. Gina has 40 feet of fencing to enclose a rectangular pen for her herd of Guatemalan guinea pigs, where one side is an existing brick wall. So find an equation to represent the area of the enclosure. So if you think about it, we've got this here. So we've got a brick wall here, and then we've got 40 what meters? 40 feet. We've got 40 feet of fencing to enclose a rectangular pen. So here's our brick wall, right, that she's going to build it up against. So we don't need to use fencing there. We just need to use fencing on these 3 sides here. Okay, so let's call, well, we know that if we're doing rectangular, we know that these 2 sides are the same. So let's call these sides x, right? So if we use these 2 sides as x, and we know that we have 40 feet to start with, this side here is going to be the 2 x sides. We're going to start with, sorry, let me back up here. We're going to start, we start with 40 feet of fencing, and then we've used 2x for these 2 sides here. All right, so for example, let's say we said that each one of these sides here were 10. This is 10 and this is 10. You would say to find this side here, I would take 40 minus 10 and 10, which would leave us with 20. If I said that this was 5 and this was 5, you would take 40 minus 5 and 5. So again, our formula for this side here is going to be 40 minus 2x, and then these 2 sides are going to be x. Okay, so find an equation to represent the area of the enclosure. So the area is just simply length times width, so we'll call that x times 40 minus 2x is going to equal the area of the enclosure, right? Okay, so to maximize this, what we want to do here is we're going to try to, basically the graph of this area here, it's going to look something like this, where this here is the maximum area. So what we want to do really is we want to, that's going to be, oops, right down the axis of symmetry. So let's distribute this through, and then we're going to actually try to find this axis of symmetry, which should help us maximize our area. So this gives us 40x minus 2x squared is our area. Okay? So in this case, a equals -2 and b equals 40. So to find our axis of symmetry, x equals -40 over 2 times -2. So we get -40 over -4. So the axis of symmetry is at 10. Okay? So that means that the area is maximized when this when one of these sides here is equal to 10. So the area is going to be, says find the equation represent. Here's our equation that represents our area. This is part A. And then find B, find the dimensions of the pen for the maximum area. So if these are 10, we'll do 40 minus 2 times 10 is 40 minus 20, which is going to leave us with 20. So the dimensions, ooh, that's terrible handwriting, sorry, are 10 feet by 20 feet. Again, that's a 10. Alright, so the dimensions that make the biggest area for her Guatemalan guinea pigs